So I'm Fraser. Thank you for coming to my talk. I live in Brisbane, Australia, and I've been traveling around Europe for a few weeks, so I didn't just get here, no jet lag, thankfully. So I'm here for a work trip, and it's very nice to be able to attach a functional programming conference to the end of that trip. So thank you to the organisers for accepting my proposal. This talk is about the Haskell foreign function interface and techniques that I have used to bind to non-trivial C libraries. The talk is not comprehensive. There'll be idioms and constructions used in C libraries that I do not cover today, but rather I'm using a library that I work on as a case study in Haskell FFI techniques. Some of the principles will be applicable to foreign function interfaces in other languages as well. So the talk starts with a story. I use Mutt for mail. So this is a console mail program. And I have used it for many years and been quite happy with it. But in my life now, in my role at Red Hat, I deal with a huge volume of mail, internal mailing lists for upstream projects, and a lot of correspondence, design discussion taking place over email. And as a result, I now have an archive of hundreds of thousands of mail messages, and the folder-based mail management paradigm just does not scale very well in that situation. So I wanted a tool like what Gmail does for mail tagging and full text search of your whole email history to easily find particular threads and messages. So there is a tool for that. It's called Not Much. And yes, it's another console program, and you can use it to index all of your mail. Build a full text search index, has first-class support for tagging. And so I've used Not Much as well for many years to index all of my mail, but it's not integrated with my mail program. So I thought to myself, right, what I really want is a program with a user interface and a mail management paradigm like what Gmail has to offer, but a Mutt-like user experience. So there's a problem, right? I already have Not Much indexing my mail, and I don't want to move away from Not Much, but Not Much is implemented in C, and there's a C library. So I could go and I could use that library to write the program that I desire, but that brings with it a whole lot of danger, the treachery of C to, this monster that rises up out of the ocean and attacks the programmer and segfaults them or whatever. So something like that is happening in this picture here. But there is hope. We can fight back with Haskell. And the end result is this program called Purebred, which is still immature, and I'm not yet using it as my main mail program, but my chief collaborator on this project is in fact using it as his everyday mail client. So it's getting to a point where it's usable as a program, and it is using a binding to lib not much written in Haskell. So covering off the very basics of the Haskell FFI. First of all, you have to ask the question, why would we want to use the FFI as opposed to writing something from scratch? Well, one of the main use cases is if you want a library or a program to do something and there's already a C library or a library that exports a C ABI written to do that thing, then the quickest way to a working solution might just be to use that C library and bind to it through the foreign function interface. This is not always a good idea. Sometimes it really is preferable to build a new library, and that way you're not attached to C and all of the baggage and the complexity and the dangers that come along with C. So it depends on the situation, and of course Haskell is a great language for building libraries from the ground up in a way that is safe and has ergonomic APIs for your users. So that's really on a case-by-case basis as to whether you would want to do that. Furthermore, if there are interoperability concerns, you say, right, this other program already exists and we want to make sure that we exhibit the same behavior as the programs using that library, well, you can use the same library. That's a good way to achieve that goal. And if you have performance critical or timing critical code, then writing those sections of your program in a language like C or FACT, as we saw from a talk just before the break about a DSL for constant time programming, then you can use those languages to write those portions of your program and bind through the FFI to them. So what does the foreign function interface look like? There's a language pragma to turn it on in your module. There are some imports of modules that export types and functions for working with the C foreign function interface, or libraries written in C. The actual foreign import is this foreign import declaration, so the third one down on this slide. And the syntax is just foreign import C-call, that's the calling convention, typically C-call, or I forget what is the one for the Windows API, but it's a different name. And then the name of the symbol that you want to import, the name that you want to refer to that routine by in your Haskell program, in this case C_sign, and then the type signature of that function or subroutine. So in this case we're importing sign, so we declare the type signature to be C double to C double. Whether or not you want to declare the result type as a pure value, C double, or an IO something, is up to the programmer writing the binding, and so you have to be aware of whether or not the routine that you're calling in the foreign library is actually pure or not. If it is, then you can just safely declare it as a pure function. If it isn't, then you should obviously have the result in the IO monad. And then finally, to use this function, you just apply it like you would any other function in Haskell. There are some tools to automate aspects of writing these binding modules. One of these tools is distributed as a part of the GHC distribution. It's called HSC2HS. The usual file extension is .hsc, and it has good support for defining the marshalling between C structures and native Haskell data types. And the other advantage is that it's already there as part of the standard GHC distribution, so you don't have to bring in any third-party tools as build dependencies for your project. Another tool is C2HS. It has many more features, but it's a separate tool, and I think its greatest feature is the automatic generation of these foreign import declarations. We will see some examples of this shortly. If you use C2HS, then you can specify in your Cabal file that C2HS is a build dependency and you require a particular version of C2HS. Cabal does know what to do with a .chs file and a .hsc file, so it's aware of these build tools, but if you use C2HS, you need to specify it as a build dependency. So an example of how to use C2HS, which is the primary tool I'll be demonstrating in this presentation. Basically, you use this curly brace hash syntax, the call hook, and then the name of the symbol. In this case, not much database open. And that's the function that you want to call, and you just apply it to the relevant arguments. After pre-processing, this will expand to something like this. So the hook with the curly pound call directive just gets replaced with the name of a symbol in the Haskell module, and it automatically writes the foreign import declaration to import the not much database open routine from the foreign library. It reads the types in the C header file and gives you a type for the Haskell binding declaration corresponding to what it has deduced from the header file. Types for pointers live in the foreign.pointer module. So pointer A is an opaque type for a pointer to a value of type A for some A. There's the null pointer value, which is just any pointer that is a null pointer, regardless of the type. And functions for doing pointer arithmetic. So, take a pointer and give me the pointer for some offset from that pointer, and casting from one pointer type to another. And of course, there are a bunch of other related functions. There's also foreign pointer, which is a pointer type, or rather it wraps a pointer and gives you the option of attaching finalizers to that pointer, so that when the foreign pointer goes out of scope, the Haskell garbage collector can schedule those finalizers to be run. So this is a nice way of dealing with objects that have been allocated by a foreign library and ownership of the object has passed into the Haskell program. So you don't need to explicitly manage this memory or be aware of the context in which this memory was allocated, but rather you can just hand control over to the garbage collector and say, when I'm finished with this object, you please clean it up. So a finalizer pointer is just a type synonym for a function pointer of the type pointer A to IO unit, that is a destructor. The new foreign pointer function, is that type signature correct, or did I write the wrong thing here? No, that's correct. So it takes a finalizer pointer, the bare pointer to the value, and turns it into a foreign pointer. And with foreign pointer lets you sort of dereference the foreign pointer, get access to the pointer inside it, and run some IO action on that pointer in a way that ensures that the foreign pointer will remain alive throughout the span of this IO operation you're applying. Strings, there's a module giving you types and functions for working with C strings. It's just a type synonym for a pointer to the C char type. Peak C string lets you take a C string and turn it into a Haskell string. With C string, takes that Haskell string, copies it to some newly allocated memory that's large enough to hold the C string, applies the given action to that pointer, that memory location, and then returns the result of that action and frees the memory afterwards. There are similar functions for dealing with, for doing the same thing but with the packed representation, so a text or a byte string. And those functions and types are provided by the text and the byte string library themselves. A storable instance defines the mapping between a foreign struct and a native Haskell data type. It has a bunch of functions. The one that we're interested in today is peak, which is has the type pointer A to IOA, which is here's a pointer to a value of some struct type. please give me a Haskell representation of this data type. There are instances of storable defined for a lot of the primitive types in the base library, including pointers. So you can actually allocate memory for a pointer, you can read a pointer out of memory, and the same goes for many other types, so ints and chars and floats and all of the things that you would expect. The alloc function at the bottom there, for a type A that has an instance of storable, will allocate enough memory to hold one value of type A, and then we'll apply some computation to that memory region and returns the result of that computation and frees the memory afterwards. We'll see how this is used again shortly. Okay, so with those preliminaries out of the way, let's look at some common idioms in C libraries and how we can use Haskell's FFI to create ergonomic Haskell interfaces to these behaviors in the C library. So the first is Enum Types. This is common in a C library for defining modes of operation, result codes, and lib not much is no different. It has a couple of different enums that are used throughout the library. This one here, not much status, is a result code type. So a lot of the functions in the library will return a value of this type. 0 indicates success, and there are a bunch of failure or error codes that are indicated by this type. So we can use the C2HS enum hook, referencing the not much status T type from the header file for the library. We give it a name, status, that we want the type to be called in our Haskell implementation. A small directive to tell C2HS how it should translate the names of the different members of that enum, and a deriving clause. So we say we would like an eq instance for the Haskell data type. And once C2HS has pre-processed the file, we get a result like this. So it's just some type of nullary constructors. The name of the type is status. The various constructors are derived from the names of the members of the enum, but with some simple transformations applied. We get the deriving clause that we asked for. And for free, we also get an instance of the enum type class. So this allows us to convert between Haskell ints and values of this status data type. But be aware that the toEnum function in this type class is non-total. So if there's an int, you try to convert it to an enum, but there's no corresponding member for that int, then this will raise an exception. So just something to be careful about using. Some C libraries expose all of the members of the structures defined by that library. Some C libraries just give you opaque pointers, which is to say the library will construct an object for you, hand you back a pointer, and then you can perform operations on that object by passing that pointer back to functions in the C library. But the structure of the data held in that region of memory to which the pointer points is not visible to the library user. So we call that an opaque pointer. Not much uses opaque pointers in its public interface. So we want to define Haskell data types that represent the different data types in lib not much, but all we have is a pointer. So in the header file, we have this typedef struct, not much database T. So the type we have is not much database T. We don't get to see what is inside it. We use the C2HS pointer hook to define a Haskell data type corresponding to this database handle. We reference the name of the type. We tell it what we would like the Haskell data type to be called, in this case database handle. And we can optionally specify that it will be a foreign pointer rather than a bare pointer, and a new type rather than a type synonym for a foreign pointer database T or a foreign pointer whatever. This results in the following code. So we get the new type, the name of the type is database handle, and it wraps a foreign pointer for a database handle. We get an unwrapping function for free. If we had not included the foreign keyword in the C2HS hook, then this would be a new type of pointer database handle rather than a foreign pointer. And if we had not specified new type, this would be a type synonym. And we wouldn't need the unwrapping function, and C2HS wouldn't write one for us. C libraries, particularly those that use opaque pointers, often use what's called a double pointer construction, a constructor. So I call the constructor function. The return type is a status code, and one of the arguments to the constructor is a double pointer. So I've allocated some memory to hold a pointer, and the constructor, if there are no issues and it can actually construct the object, will allocate some memory, construct the object, and then write into that region of memory that I've allocated to hold the pointer to that memory. And in doing so, passes ownership of that structure to the calling code. So the not much database open routine takes a path to the not much database, takes a mode, and this double pointer to actually hold the database handle. So in Haskell, we can open the database. Using the database open function, we use the alloc function that uses the storable instance to allocate memory to hold the pointer. We call not much database open. We inspect the result to see if it was a success or not. If it was a success, then we peek the pointer to actually read the pointer out of that memory we allocated, wrap it up in a foreign pointer, and that's the result in the write constructor. And if the return value from not much database open was not a success, then we just return left E for the status code that was returned. So we can signal that the operation failed and this was the failure code. Iterators in C often produce an iterator structure that the caller owns and then calls repeatedly routines to test whether that iterator is still valid. Does it have more to give you? If so, please advance the iterator and return the value at the next position. So again, lib not much uses this idiom. So we have a not much message get tags is actually going to give you a iterator for the tags of a message. And then we have functions to test whether that iterator is still valid to get the current tag and to advance the iterator. An ergonomic interface for an iterator will just be a list of strings, well, strings representing tags in this case. So this tags to list function is a recursive function that just tests the pointer. If the pointer is still valid, then we'll fall to this second case where we cons the current value from the iterator onto the rest of the list. So we need to get the pointer, call some constructor, in this case peek C string, and then advance the iterator and return the value from the constructor. And at the point where the test function indicates that there is nothing left in the iterator, we terminate with the empty list. So that's how you can turn a C iterator involving multiple functions into a Haskell string, or a list of Haskell strings, or a list of Haskell whatevers. For dealing with macros in C files, well, the CFFI can only bind to what is in the object file. So if you have a function that is actually not a function but a macro, you've got a couple of options. One is that you can actually bind to the non-public API and wear the risk that at some point that API could change. And you'll have to do some maintainer busy work to keep up or maintain different implementations in your code to support the different versions of the library. Alternatively, you can write some C bits for your Haskell project that use the public C API, which can use the macro, and expose a new symbol in an object file in your Haskell project and bind to that instead of directly to the foreign library. And that approach works well and is arguably a better decision if you're going to do long-term maintenance on this project. For managing external object lifecycle, so I already mentioned that foreign pointers are useful for allowing the Haskell garbage collector to take care of finalizing foreign objects. So here we have the constructor and the destructor for a not much query. In Haskell, we can use query create to create the query object. So we have to use with C string to turn the Haskell string into a C string with database handle to unwrap the database handle that we have. Then we can call not much query create and take its result, lift it up into a foreign pointer, attaching the query destroy destructor in that foreign pointer. This foreign import declaration with the ampersand there is importing a function pointer. So rather than an actual routine that we can call, this is just importing the address of this function, which is what we need to have a finalizer pointer that we can attach to a foreign pointer and allow Haskell's garbage collector to call. But beware, if there are hidden references in derived objects back to the parent object, and this may not necessarily be obvious from the API itself, then if the parent is freed, you could have dangling references in the child, and you'll end up with, at best, a segmentation fault, and at worst, some kind of undefined behavior. And if you have a library that uses a fancy allocator, like talloc, which is a hierarchical allocator, where if a parent object is freed, it will actually free any of the child pointers associated with it, then you'll need to do some tricks to work around this situation so that you can actually take advantage of Haskell's garbage collector in managing these foreign objects. In the Haskell not much binding that I maintain, what we do here is we, every time we construct an object, we essentially call some talloc routines to detach it from its parent and make it its own top-level object so that it'll never get freed when a parent object gets freed. So, now that we have the basic shape of our API and we've implemented these Haskell functions to expose ergonomic APIs and ergonomic types, where the underlying C routines maybe aren't so nice to use, we would like to leverage Haskell's type system to enforce the correct use of the C API insofar as it is possible to do so. So the first area that we can address is working with read-only versus read-write databases. Lib Not Much lets you open a database, either read-only or read-write, but of course some routines can only be used with a read-write database. For example, Not Much message add tag needs write access, otherwise it will return an error code. We don't want our library users of the Haskell Not Much binding to have to deal with this situation if we can actually rule it out at compile time using the type system. So we have an enum hook to give us a database mode type. I don't know if I included the actual definition, but there's Not Much status read-only database and Not Much status read-write database are the two members of that enum. So that gives us this data type and the corresponding enum instance. Then we can use data kinds and now parameterize a new type called database over the database mode. And with the messages and threads and the other derived objects, we propagate this phantom type information along. Then we can define our functions that require read-write databases to work properly, as defined over message read-write, as opposed to message A or message read-only. In this way, we can ensure at compile time that functions that require read-write access can only be used with a database that was opened in read-write mode. And in some cases, such as message add tag, this actually allows us to completely remove the error conditions from the API. So we can statically rule out now that this function can actually fail in any way, so we just return an I/O unit, making the API a bit nicer. Another concept in Lib Not Much is one of locking or freezing a message. So if you want to do a number of tag manipulations, so remove some tags and add some other tags all at once, you can freeze the message, perform these operations, and then thaw it. And any other programs or threads that have the database open will not see any of these changes until the message is thawed. So basically giving you some atomicity. So the functions are Not Much message freeze and Not Much message thaw. So what we can do here, just add more type parameters to the message data type, a type level nat to represent the frozenness of the message. So message 0 mode is a message that is not frozen, and if you freeze it, you get a message 1 database mode. Add tag can be used at any level, so it's just defined as a message n read-write for any n. Freeze takes any message n and returns a message n plus 1, so increasing the freeze level, and message thaw decreases the freeze level but also has a constraint that the message was actually frozen to some degree to begin with. And so that allows us to guarantee the correct use of the thaw and the freeze API from within our Haskell program. Performance considerations, you can use the unsafe keyword, which sounds scary, and it is a little bit scary, but it's usually safe to use unsafe. And it basically instructs the Haskell runtime system that it doesn't need to do some additional bookkeeping for this function. You definitely need safe, which is the default. If the C routine you're calling can call back into the Haskell runtime system, that's the main reason you would need to use safe. And in some admittedly pathological cases, it can actually give you a big speed up. So this is for iterating all of the tags in the database of 160 odd thousand messages. and it almost doubled performance just by using unsafe, because it's this this iterator paradigm where we're calling C functions over and over again to test the iterator, advance the iterator, get the current value at the iterator. So avoiding that bookkeeping results in a big performance improvement on a particular kind of use of a C API. So you won't always get a result like this. There was actually a bug that caused me to do some further reading, and there's another situation where you cannot use unsafe, and that is where the C call could block. And in that situation, you need to use safe, otherwise you could end up blocking the entire Haskell program. Lazy iteration, we just add a healthy dose of unsafe interleave IO, and this means that we can suspend the execution of these iterator functions in C. The obvious benefit is if you are iterating a large iterator but you're only interested in the first few at the beginning, you can avoid doing all of those C calls. You're only going to do those C calls sort of as you're trying to pull values off the front of the Haskell list. So for searching the whole database but only counting the tags of the first 10 messages, we see a dramatic speed up, as we would expect. The more subtle benefit is that if you're only traversing that list once, the garbage collector can kick in, and you're going to have substantially lower maximum residency in that program, or for that operation at least. And that can result in a performance improvement on the clock, but also lower memory usage. So those are the main things I wanted to show you. We didn't cover foreign exports, so how to actually define your functions in Haskell and make them callable by foreign code. We didn't talk much about how to define the marshalling between C structures and native Haskell data types, because live not much, the case study here, is using opaque pointers. We didn't talk about other foreign function interfaces for Haskell, for example, for the JVM FFI in ETA or JavaScript in GHCJS. And there are some other performance optimizations or potential performance optimizations like interning and so on that I did not cover. And with that, I hope there's time for a couple of questions. There's a mic coming.
Oh, sorry. Thank you very much for the talk. So is the resulting library available as a Haskell library that I can use to kind of automate the MUT for myself, or is it, or the indexer?
So automating MUT for yourself, did you say?
Not the MUT itself, but it's the indexer part, right, which you integrate with the mail client. Yeah,
so the Haskell binding is on purebred MUA/HS not much on GitHub. So if you just want to do stuff with the not much binding, that's where to find it.
I could kind of implement my own extension of indexing my mail or something like this, or what would be the use case?
The use case would be you want to do something with mail in a not much database already. So this is very much just a binding to the not much tool. Yeah. If you wanted to index your mail differently, then you would use a different tool or write a different tool.
I see. Yeah. Well, thanks a lot. Yeah.
Great talk, thanks. Do you have resources for these topics that you didn't cover, specifically performance?
So check out EdCommet's intern library if you're interested in interning. I actually did some experiments. It turned out not to be worth it, because the main thing that you would get a benefit from interning is tags, in that there are typically a smallish number of them in your entire database, and they're used over and over again. But the overhead, because they're so small, a short string inbox or red or whatever, the overhead was such that there was no real benefit to using interning. And the other thing is avoiding unnecessary string copies. So the technique there is rather than copying a C string to a Haskell byte string or a Haskell structure without the null terminator, like maybe you just define a new type, keep the null terminator, and then when you need to use it again in the foreign library, you can just just hand the pointer straight over. As long as you make sure that you're going to keep that alive, then you can avoid the copies. So it's these sorts of techniques. I don't know of any resources that kind of gather them all into one place.
We would have time for one short question, but what's the
I think you maybe mentioned this already. What do you do with objects returned from the foreign library in terms of the lifetime management? Like you put them into the Haskell garbage collector, which guarantees they go away. Was there a timeliness guarantee on forcing them to go early, like scope destructors?
No, there isn't. So if you want prompt finalization, use a library or an approach that gives you prompt finalization.
Okay.
Okay, thank you.